For problem number 3, when we're looking for the derivative, the first thing I'd want to do is rewrite this as 4 times x to the negative first power. It'll be easier to complete the derivative once I have the x out of the denominator of a fraction. And then f prime of x is going to be, oops, I don't know what I did there. We'll fix that. F prime of x, there we go, is going to be 4 times negative 1 x to the negative 2 power. So we can just write that as negative 4 x to the negative 2. All right, number 4, we have to break it down by parts. So remember, each plus or minus sign, each addition or subtraction symbol on these problems here is like a separate differentiation. We differentiate by parts basically. So we look at the first one, that is x squared. We can rewrite that as 2x to the first. The second one would just be 7. And so it's like 2x to the first. The second one would be 7 times 1 x to the 0. And the third one would be 6 times 0 x to the negative 1. And what happens is that simplifies. It's just going to be 2x plus 7. And the 6 is going to go away completely because we're multiplying it by a 0. Alright. Problem 5, very similar. F prime of x is going to be negative 4 times 5, so that's negative 20, x to the fourth, plus 3, and then the 2 goes away. Problem 6, we can rewrite this as 3x to the negative 2 plus 7x. And then this becomes 3 times negative 2, x to the negative 3, plus 7 times 1, x to the 0 power. And that becomes negative 6, x to the negative 3, plus 7 when I show all my steps there. That's the idea for these types of problems. That's part A for each of these. Are there any questions on those?
Okay, why do you do it like twice after, like for the fraction ones, why do you do it multiple times?
What do you mean by do it multiple times? Which one?
Like for number 3, wouldn't it just stop at 4x negative 1? Like why do we continue after that? Like what is that?
Oh, so I'm just showing the intermediate step basically. So what happens is rewriting it as 4x to the negative 1 power is not taking the derivative. That's just rewriting it, because anytime you have a number in a variable in a denominator of a fraction, you could technically rewrite that as a negative exponent. So all I've done at the very beginning here for number 3, that's just rewriting it. So that's still f of x. I haven't taken a derivative yet. And then when I take the derivative, it changes from the negative 1 power to the negative 2 power.
Oh, okay, thank you.
That's what's happening there. Okay, so the first step was literally just changing the form, so I could take the derivative a little easier. Okay, next up, part B. Now we're going to find f prime of 3. So for the first one, it's 10 times 3, 30. And we can answer part C at that same time. Part C asks, identify if f is increasing or decreasing at x equals 3. Well, if part B is a positive number, positive 30, that means it's increasing. All right, so that's how we can tell. So look at the derivative when we plug in that value, and if it's a positive number, it's increasing. If it's a negative number, it's decreasing. If the answer happens to be 0, then it's neither. It's a slope of 0 at that point. All right, that's the idea with these particular problems. Part B, f prime of 3 equals negative 12 times 3 to the negative 5th. All right, so that's going to be negative 12 over 243. So it's going to be some real small negative number. I'll just leave it at that for now. The important thing is that for part C, we can see this is decreasing at that point. All right, because it's a negative number. And you could put that into your calculator and get some really small decimal answer. I'm just going to leave it as a fraction, negative 12 over 243. Okay. Part 3, I'll show you. So I kind of did a sneaky thing there for number 2. So I'll show you what I did there. Whenever you have a negative exponent, remember you can put it back as 3 squared. And that's kind of what I did for part B. I wrote it as negative 12 over 3 to the 5th power. That's how I got it back into a fraction form. Just if you were confused about how I did that. So this becomes negative 4/9, which I think if you put in your calculator is like negative 0.44444. So that's what happens for part 3, for number 3 here, for part B. And then C is decreasing because it's a negative answer again. Okay. Alright, this one's not too bad. 2 times 3 is 6, plus 7 is 13. So positive 13, positive number. That is increasing. That's how we tell by looking at it. We can always graph the original function and look for the line x equals 3, but it's kind of hard to tell sometimes if it's increasing or decreasing. The derivative is going to be a lot easier to tell because if you graph the derivative, then you can see when the derivative is positive, it's increasing. When the derivative is negative, it's decreasing. That's where the derivatives come in very handy for us. Alright. Alright, so this one becomes negative 20 times 81 plus 3. So 10 times 81 is 810. 20 times 81 is 1620. So negative 1620 plus 3. So we should end up with negative 1617. And because it's a negative number, that is decreasing. And then last one, problem 6, negative 6x to, oops, we'll do f prime of 3, sorry about that. Negative 6 times 3 to the negative third plus 7. So that's really negative 6 over 3 to the third, which is 27. So I get negative 6/27 plus 7. And that's going to be some really weird number, not fun, but it is a negative number. So I'm going to say that one is decreasing. But yeah, I can't do that one quickly in my head, so I'm just going to leave it at that for now. But that's the idea with these problems and their derivatives. There was a lot of practice on the homework yesterday for these types of problems. But that's really the key for chapter 12. Can you take a derivative? Can you identify whether the function's increasing or decreasing in value? That's the big thing. Okay? We're going to go a little bit more in depth, but that's about it. So if you guys are feeling okay with this for chapter 12, next week's going to be a breeze. Just to give you an idea for next week, I think we're going to shoot for the chapter 12 assessment on Friday next week. So that way we end with 2020 with the differentiation all done. And then we'll come back from winter break and we'll do some derivatives review when we get back from winter break. And then we'll start chapter 13, which is integrals, which is basically if I give you a derivative, how do you undo it and put it back into a function form? So it's like working backwards. That's what the last chapter, or chapter 13 is. And the only to be pretty quick and straightforward. We have one example, and it's just today's assignment is going to be real world problems. So how do we deal with these derivatives and situations in real world, and what are they telling us, for example? So first, the problem, example 2, part 1 says, in economics, the marginal cost is the cost of producing one more unit. this can be approximated by the gradient of a cost curve. So it's saying you can do this by finding the slope, okay, of a curve. So if we know the equation for the cost of something, we can actually take the derivative of that cost equation, and that's going to give us something called the marginal cost. And the marginal cost is the cost for producing like one more unit. Like how much does it cost like per unit basically. So that's what we're looking at here. So the first thing it says, a company produces motorcycle helmets and the daily cost function can be modeled by this. So it's C of x equals 600 plus 7x. Oops, I'll rewrite it down here because it's on two separate lines right now. 600 plus 7x minus 0.0001 x cubed. And it says for 0 is less than or equal to x is less than or equal to 150. First, we want to identify x. That's the number of motorcycle helmets. So what this part right here is telling us, we have to put that into context. That's saying that this company produces 0 and 150 helmets per day. All right, that's what this part tells us. All right, so that's the first part. C is the cost in US dollars. All right, part A asks us, write down the daily cost to the company if no helmets are produced. No helmets. So what that means is, hold on, wait, a question here. Okay, yeah, good. All right, so if no helmets are produced, what we do is we take our cost problem and we plug in 0. And we get 600 plus 7 times 0 minus 0.001 times 0 cubed. So it just comes out to $600. So it's saying if this company doesn't produce any helmets, it's going to cost them $600 a day. That's how much money they lose. All right, so that's for all of their overhead expenses or whatever. Okay, that's the first part. The next thing this problem asks is find an expression for marginal cost. So it tells us C prime of x. So basically we want to take the derivative of the original equation. So I want you guys to go ahead and try and take the derivative of this equation now to find the new equation. So you don't need to show all the steps like I did, like where I did part 1. I'm just showing you how it breaks down. You don't necessarily need to show those steps. If you know the 600 is going to go away, then just the 600 goes away. But 7x would just become a 7, and then the 0.0001 x cubed is going to become a 0.0003 x squared because we're multiplying it by 3. And we're dropping the variable by 1 degree, 1 power. All right, so that's the first, that's finding the derivative. And this is the equation for marginal cost now. Now it says find the marginal cost of producing 20 helmets. So part C is saying, okay, this is how much it costs for 20 helmets. So we plug in 20 and we solve. And then part 2, find the cost for 80 helmets. So go and plug in 20 and 80 and solve for these. When we find the cost of 20, I came out to like 6.88, and the marginal cost of 80 helmets, we got 5.08. And then part D just asks, state the approximate units for the marginal cost. So what's that telling us? And what that's telling us is the dollars per helmet. So what it's saying for the marginal cost for part C is saying it costs $6.88 per helmet when we're producing 20 of them. When we produce 80 helmets, that cost drops to $5.08 per helmet. Okay, that's the idea. So making sense of the real world situation, that's kind of what's going on here. So that's what marginal cost is. And this is actually how this is calculated for like companies like this that make bike helmets or something like that. Companies do have costs and marginal cost tables, and they have to use differentiation to find those values. This is a very simple version of it, but these are this is why calculus was created, was for problems like this. Helps companies optimize their cost tables and stuff like that. All right. Part 2 says a hammock can be modeled by the function f of x equals 2x cubed plus 3x minus 4. I don't know why I put 2x cubed there. That is a mistake. That should be 2x squared. All right. A mosquito traveling in a straight line gradient of 11 touches the hammock at point A. So when it says a straight line gradient, that's slope. All right. Find the coordinates of point A. So we're looking for a point specifically on the graph. So if we were to graph this 2x squared plus 3x minus 4, it's going to be a quadratic function. Like something like this, and we're looking for like point A, we're looking for, hey, when's that slope 11? That's a really steep slope, so we're looking for something like this, that one tangent point there. All right, that's the idea for this problem. So in order to find the coordinates of A, the first thing we got to do is we got to find the equation of the line. So we'll find f prime of x. So we take 2 times 2x plus 3 times 1, x to the 0, minus 4 times 0, x to the negative 1. So in reality, this becomes 4x plus 3. That's our slope equation. All right. Now, what happens is we know it has a gradient line of 11. So what that's really telling us here is it's saying f prime of 11. Or I'm sorry, it's not saying f prime of 11. It's saying f prime of x equals 11. So that's what it's saying when it has a straight line gradient of 11. So what we want to do now is we want to plug in 11 and solve for x. That's the idea for this particular problem. So when I give you the slope or the gradient, you actually want to work backwards and figure out what x is. And we go and subtract 3 from both sides. And we're going to get, 8 equals 4x. And then we divide both sides by 4. And we get x equals 2. So what that's saying is when the slope is 11, the x value of our point on the graph is 2. So let me zoom over here real quick. So again, it's saying at point A now, the x value is 2. But we still need to find the y value. We don't have the y value because we know the slope is 11, but we don't know what the actual y coordinate of the point is. So any thoughts on how to find the y value if we know x equals 2? How do you find a y value of a curve?
Plug it back in.
Yeah, we plug the x back in, but we plug it back into the original equation because we're going to find the y value of this curve now. Exactly. So I'll change colors here. It's going to be f of 2 equals 2 times 2 squared plus 3 times 2 minus 4. Yeah, so because we knew the derivative was the same as the gradient of the tangent, that's how we were able to set that equal to 11. And then we were able to find our x value, plug that all back in, and we get our y value, and we get point A is 2, 10. And that's our solution for this particular problem.